Oh, I need to share my, so welcome to day 2. Okay, so let me recap a little bit where we ended up. So what we had was, we were looking at, well, a differential equation, except, well, it's really, since we didn't want to deal with connections on vector bundles, we pretended this was just a rational map with, a matrix with coefficients that are rational sections of the sheaf of differentials on whatever curve we're over. And we turned that into a sheaf M on a ruled surface which basically looks like, which comes from the vector bundle structure sheaf plus anticanonical sheaf. Now, I might have gotten that wrong. It might be the dual, but luckily those give us the same surface, so we can, it doesn't actually matter which one we get so much. Okay, but, and so we have this procedure, and remember it involves factoring A as something like B infinity inverse B0. And I should say here, there are multiple conventions one could take here. And so naturally, I'm sure I've gotten it wrong. But this is, any factorization along these lines, the same sort of procedure will work. It's just a question of what you end up with at the end and whether certain functors are covariant or contravariant. But all the actual conclusions are the same. Okay, so what I didn't talk about is, where do the singularities fit? In this setting. So remember, we don't just want to classify equations, we want to classify equations with specified singularities. And so if we're going to do that, we really need to know what this sheaf transformation does, what this translation does to the singularities of the equation. Okay, now the first observation is that if A is singular, we're talking about a differential equation, modulo the relaxation part. We're talking about a differential equation. So its singularities are where the matrix has poles. And because we factored this so that it has zeros and poles in different factors, the poles all live inside B infinity. So the first answer, the equation is singular where the determinant of B infinity is equal to 0. Okay, so far so good. But what does that mean in terms of our sheaf? So our sheaf, remember, is we're basically taking B infinity wrong. Oh, yes. So we're taking, well, so let me remind you what this ruled surface looks like. So, okay, I'm going to pretend that C is P1 because, well, that's the most interesting case anyway. And you can be a lot more explicit about it. So then X almost looks like a weighted projective space. So basically it has generators Y, X, and W, where Y has degree 2 and X and W have degree 1. This gives us a perfectly reasonable graded algebra. And then we take proj of that graded algebra. Now, this isn't quite right because weighted projective spaces are a little annoying. And there's a reason why Hartshorne assumes things are generated in degree 1 before allowing you to take projes. Weighted projective spaces are singular, unlike normal projective spaces, or typically singular at least. And here, the singularity basically comes from X equals W equals 0. And essentially comes from the fact that you can negate y then without changing anything because, or sorry, you can negate both x and w without changing anything. So there's sort of this invisible symmetry, and that's getting turned into a singularity. And so what we actually do is take this weighted projective space and resolve that singularity. And now that's very simple. It's just you blow up the point x equals w equals 0 on this weighted projective space. Okay, so that's what x looks like. And the point is that we can therefore pretend that x really is just this weighted projective space to a fair extent. Okay, and then what we find is that our equation, our matrix B on X looks like, so I think I've gotten this right now, B infinity Y minus B0. So basically the way we should think of this is Y is basically playing the role of the derivative. And this, so we're just sort of translating our equation into poles times derivative is equal to zeros times our vector. Okay, where of course B infinity and B0 now have been homogenized. So, and the main difference here is that B0 has degree twice, it has degree 2 more because we need to cancel, we need to make this homogeneous overall. So this is what B looks like. And so therefore M is the co-kernel of this. And this tells us therefore that oh, sorry, I think I did get this wrong. Y is like 1 over the determinant. As I said, give me 2 choices, I will always get the wrong one. So M is the co-kernel of this map. But this tells us, this lets us actually recover information about the singularities, because if we look at where Y equals 0, well, this is the co-kernel of B infinity, appropriately homogenized. And this is, of course, is supported on the locus where the determinant is equal to 0. And if you look carefully, this really is the right thing. This does the right thing at infinity. So this really is the, once we've homogenized properly, this really is the right thing to do. Okay, so this tells us where the singular points are. But we really want to say a little bit more. We want to know more than just where the singular points are, because after all, even in the simplest case where it's Fuchsian, just knowing where the singular points are doesn't give you enough information. You also need to know what the exponents are. And the beautiful fact is that in the Fuchsian case, i.e., if B infinity inverse has the most simple poles, the exponents are recorded, are in the restriction of M to the non-reduced curve y squared equals 0. And basically the point is y then is y you can think of as an infinitesimal, and so it's this really is giving us residue information by sort of looking at what this equation looks like, mod y squared, and focusing on just the gross thing of, okay, where does this vanish? Well, it vanishes where B infinity is 0, and then given that B infinity is 0, well, B0 times y has to be 0, and so and that gives us a little jet, a point with a direction, and that gives us. And if B infinity has a multiple 0 compatible with that simple pole, but that the rank drops by more, we get multiple jets, one for each non-zero exponent. So the upshot is, that in the Fuchsian case, the singularities of A gets translated to the sheaf M restricted to y squared equals 0. Now you can start to see why I've been saying that things get more complicated the easier they are for most integral systems people to deal with things. The differential case is, of course, where everything started, and we're looking at this non-reduced curve that things are living on. But them's the breaks. I mean, you have to do something like that. You have to have something non-reduced if you want to have any hope of really getting differentiation to happen. So that's where this is happening. Okay, so the summary, we get a dictionary from, on the one hand, Higgs bundles with specified singularities. And on the other hand, sheaves on our weighted projective space, or more generally ruled surface, with specified restriction to a particular double section. That is, a non-reduced double section. So we just take a section and then square its equation, local equation. Okay, so this is what happens in the differential case. Now, I'm palming a card here because, sure, in the Fuchsian case, you can check that indeed the restriction of m to y squared equals 0 tells you everything about the singularities. But, there are worse singularities out there. And so you have to worry a little bit about whether that you really do encapsulate the information. But we'll see eventually that, in fact, you can classify basically what happens when y on this for this restriction, and use that to actually directly show that yes, this tells you everything you want to know about the singularities. Okay, so now let's talk about a difference example. And the simplest example to deal with is the elliptic difference case. So example 2 of this translation to sheaves is elliptic difference equations. So now, remember, an elliptic difference equation looks like something like this, where A is, we have some point, we've chosen a point in our curve, and A is in, is an n by n matrix over our elliptic curve. Now, I should say a little bit about what a connection is, what the analog of a connection is. So connection is a map from V, a rational map from V to, again, there's two choices, so I'm probably going to get the wrong one, but basically from a vector bundle to a pullback of that same vector bundle by our translation. And so this is the right analog of a difference equation when we allow it to be a non-trivial bundle. And it's worth noting that in this case, and basically anytime we're over a higher genus curve, trivial bundles are actually kind of rare. I mean, over P1, the trivial bundle is, a fairly typical bundle. And in particular, if you look at if you classify bundles, there's this doohickey called the moduli stack of bundles, and the trivial bundle is open in that thing. So it has a lot of degenerations. But if I just hand you a random bundle, it's probably either the trivial, and it has the right degree to be trivial, it'll be trivial. Whereas this fails in higher genus, because you always have infinitesimal deformations of the trivial bundle that make it non-trivial in interesting ways. So, so you really need to talk about connections in general, even if you you don't have this excuse of being a matrix on an open set. Okay. The other thing I should say is that for differential equations, there's a perfectly reasonable algebraic geometric way to talk about connections, which is to say, okay, I want something which is locally a matrix form differential equation. And so you say, okay, I have this one open set, I have a matrix equation. I have this other open set, I have a matrix equation. And where they overlap, I have a change of basis that's holomorphic on that open on the common intersection. And you just glue everything together. And if you trace through the definitions, that ends up being equivalent to the definition of a connection from differential geometry. Basically a Gaga-y kind of thing. So you get the same notion of a holomorphic connection in a differential geometry setting is the same as something which is locally a matrix equation. Now, for difference equations, this kind of breaks because we have this translation in the picture, and there aren't, in general, any invariant open sets. So, you'd like to be able to say, okay, I have this equation on an open set, but if it's not invariant, what do you even mean by translating by Q there? And there's a way of getting around that, which is a little technical, which is basically just say, okay, well, rather than taking an open set, we'll take an intersection of open sets, a countable intersection of open sets. We'll just basically omit some orbit or some collection of orbits. And there, because you've omitted an invariant closed subset, or sorry, an invariant union of closed subsets, you get something which is, well, on the one hand, it's actually still a scheme because you just inverted a lot of points. So you've inverted a lot of divisors on your curve. So that you still actually get a perfectly reasonable scheme. And in fact, it's going to be an affine scheme in general, as long as you omitted at least something. So you get a perfectly reasonable scheme, and you can choose what the points you omit so that your vector bundle becomes trivial. And with a little bit of work, you can actually cover, you can show that you can do that with a covering. And then the only issue is this is not an open covering. It's a covering by localization, basically. But it turns out to be good enough to let you still glue things together and have sheaves still make sense. So you can still, for instance, build a vector bundle by specifying, a change of basis between two such complements. That means between the trivial bundles on two such complements. And so you can get a reasonable notion that way. But in the end, what you find is when you do that, you just get this notion of, hey, I'm just vector bundle to a pullback of the same vector bundle. Okay, so the Higgs analog well, what is that? Well, there we basically say, okay, well, I don't want to pull back by Q. So let's just pretend Q is the identity. Okay, so we get a meromorphic matrix, or an invertible meromorphic matrix. So we actually get back to just essentially the matrix thing, except of course we've got this vector bundle in the picture. Okay, and then we can factor. And that gives us now a matrix B going from V to 2 copies of V. And this becomes B going from V to rho lower star, rho upper star V, where rho is, again, the ruling of a ruled surface. In this case, it's a trivial ruled surface, just E cross P1, but that's okay. And thus we get, sorry, again, there's a twisting by 1. And so the end we get base, or sorry, there should be a W. And so the end we get a matrix B from rho upper star V twisted by a class of a section, which we could take to be one of the 2 elliptic curves, to sorry, we can take to be a fiber of E cross plane 1, so just a copy of E, to rho upper star W, and then we take the co-kernel, and that's M. And the same translation, the same argument tells us, yeah, we can reverse this procedure. And given an M coming from this procedure, we can recover A by just doing everything in reverse. Okay, and then finally, what are the singularities? Well, the singularities are zeros of B0, of the determinant of B0, and the determinant of B infinity. Or I should say, of course, they don't have to be a zero of both, they just need to be zero of one or the other. But we should, of course, remember that there's two flavors of zeros. There's zeros and poles, and so we should not just take the product of determinants. That's bad. And in particular, what we see is that the zeros are encapsulated by M restricted to, let me say, y equals 0, and the poles are M restricted to y equals infinity, where y is the coordinate of P1 in E cross P1. So the upshot is we can combine this information and we see that there's two copies of E that we're restricting to, and the singularities are recorded by the restriction of the sheaf to those two copies of E. Okay. So this is another relatively simple case. And then we can keep going, so what you'll notice is that so for the other difference cases, you'll notice that something slightly funny happens, basically because it's no longer just a trivial ruled surface. And so what happens is we still have two copies of the base curve. Now the base curve is P1 because additive or multiplicative group compactifies to P1. And so what we find is that in the nodal case, we have two sections, but oops, sorry. Let me draw this correctly. We have two sections, but they meet at 2 points. And those 2 points are exactly the points corresponding to 0 and infinity in the P1 over which our difference equation lives. Okay, so this is the multiplicative case. And what that corresponds to is exactly the fact that what it means to be singular is more complicated at 0 and infinity than just saying that B infinity or B0 has that it has vanishing determinant. So, and you can check that indeed, if B0 and B infinity don't agree at 0, and sorry, they're forced to agree at 0 because of the way. Well, we'll talk more about that, but so the factor is the slightly tricky thing is that B infinity and B0 must agree at 0 and infinity for this to work properly. Because if they don't, because if A is not the identity at 0, our equation is singular. Now, it's okay to force B infinity and B0 to agree at 0 because they are allowed to vanish at 0. And so we can always, just by throwing in extra zeros there, we can always arrange for it still to be a legal any factorization can be turned into a legal factorization. And then just a question, and then we just want to do it again in a minimal sort of way. Okay, and so in particular, if B0 and B infinity vanish, then at 0 or infinity, then we pick up an extra. We still have a singularity, which may just be coming from the fact that, our equation looks like v of qz equals alpha v of z, where alpha is not 1. So we get a slightly more complicated curve that we're restricting to, but that's because what it means to be singular is somewhat more complicated. And then the other case we understand, the additive case. So this, of course, again, is Q difference, is ordinary. And so there, the two components are tangent, corresponding to the fact that B0 and B infinity are supposed to agree to second order at infinity, because A is supposed to be the identity to second order at infinity. Oops. Now, so far so good. But there's a common thread, which tells us that we're missing cases. So the common thread is in each case, we have this curve, and we have this ruled surface, and that ruled surface is always that same ruled surface we saw in the differential case. Remember, so, for instance, if C is elliptic, omega C is trivial. And so this is OC plus OC, which gives us C cross P1. And you can check that in these cases, if you sort of look at what this means for them to agree at 0 and infinity, that sort of tells you that their difference, again, basically has degree effectively lower by 2. And so once you take that into account, you're again left with the same ruled surface, this weighted projective space, basically. So in each case, so we always get this, and the singularities corresponds to the restriction to a curve Q. And this curve is always anti-canonical. So it's a divisor such that minus Q is the canonical, it represents the canonical bundle. Okay, and you can check in each case, we sort of, once you figure out what the divisor is supposed to be, this is the common thread. So this tells us two things. Firstly, it tells us that we should explain this. And secondly, it tells us that when C is P1, there should be more cases. So let me first explain this. So why is this the case? So this is going to be a partial explanation based on the fact that I've already said there's non-commutative geometry in the picture. So we should expect, in general, this whole picture should deform to something which we should be able to call a non-commutative surface. But we've taken this non-commutative surface and we've degenerated it to a commutative surface. Whenever you do that, there's actually an induced structure on the commutative surface, a residual induced structure. And this actually holds for a general scheme. So particularly in the affine case, so let A be an associative algebra over a power series ring. And traditionally, the variable of that power series ring is called H bar. Yeah, you can tell physicists got involved in this. Okay, such that if we mod out by h bar, the algebra becomes commutative. So this is locally what you expect a degeneration of something non-commutative, something commutative to look like. Okay, so on A, there's a natural Lie algebra structure. Well, let me give this a name. Let me call that A0. Is there A mod H bar? So basically, we should think of A as giving us a formal non-commutative deformation of the commutative algebra A naught. So on A, there's a natural Lie algebra structure. Because, well, any associative algebra has a natural Lie algebra structure. So we just define the bracket of x and y to be the commutator of x and y. And so this satisfies x bracket x equals 0. Moreover, it's a derivation. And it satisfies the Jacobi identity. Okay. And so this is, any associative algebra has this. But because we have this degeneration to a commutative curve, there's an induced structure. I should say, of course, this property that it's a derivation is not part of the Lie definition of a Lie algebra if you're not familiar with Lie algebras, but it's very important for our purposes. Okay, so there's an induced structure on A0. Namely, we define the bracket, the curly bracket of x and y as follows. We take x and y, which are, remember, in a quotient of A. We choose lifts of them to A. We take the commutator. We divide by h bar, which we can do because A commutes mod h bar. And then we set h bar to be 0 to give us, again, an element of A naught. Okay. No, I see. Spelling got away from me there. Okay, so we get this induced structure, and it's easy to see that this new bracket, well, still satisfies x bracket x equals 0. Oh, sorry. The first thing we need to check is, yes, this does not depend on the choices, and that's because if we add h bar times something to y hat, well, they commute. The difference over h bar commutes with x hat mod h bar, and so everything cancels out, and we don't actually affect the answer in x naught. Okay, as bigger, this satisfies. It's alternating. It's a derivation in, well, let's say the first argument, but of course, since it's alternating, it's also antisymmetric. If I could say, of course, this is also it's also bilinear over the center. So particularly, since we have this k in there, it's bilinear over k. Okay, so it's alternating. It's a derivation in either variable, either argument, and it satisfies the Jacobi identity. And so this structure on a commutative algebra is called a Poisson bracket. And the general theorem that I've basically told you how to prove is that if you have a family, if you have a flat family of non-commutative algebras, I mean, of course, we're doing algebraic geometry, everything should always be flat. So basically, if it's free over K bracket H bar, you get this, if you have a flat family of non-commutative algebras that degenerates to a commutative algebra, and it's a one-dimensional family, if it generates to a commutative algebra, there's an induced Poisson bracket on that commutative algebra. And we should note that if A mod H bar squared commutes, this vanishes, so it's not very interesting. But we could still get a Poisson bracket by dividing by H bar squared. To get a new bracket. And so for some power gives a non-trivial, a not identically vanishing bracket. Unless of course A is actually a family of commutative algebras. Okay. So far so good. Now we have to be a little careful. It turns out that non-commutative geometry is, or at least non-commutative algebraic geometry for these types of surfaces we need to deal with for the still theory is way more algebraic than it's geometric. In particular, we're used to thinking of schemes as being glued together out of these affine pieces. This actually does not work for non-commutative geometry in general. It really doesn't have that kind of local structure you can play with. However, we can still hope that this infinitesimal version of a non-commutative structure, the Poisson bracket, would behave in a more local fashion. And so particularly, it's easy to find a Poisson bracket on a scheme. So a Poisson bracket on a scheme X is a Poisson bracket on each affine open and agreeing on overlaps. So to make sure that this makes sense, the only thing we have to actually check is that if you invert something, you get a natural induced Poisson bracket on the localization. So if you have a Poisson bracket on two overlapping affine opens, you can in fact restrict the Poisson bracket to the common intersection and insist that they agree. So that's again, the natural way of defining it. But there's another way of getting at it, which is a little more global. So remember, what do we have? It's an alternating biderivation. So what is an alternating biderivation? Well, a derivation, we have this universal object, the sheaf of differentials for derivations. And so the universal object for alternating biderivations is just the exterior square. So we get a map from, we want to, so a biderivation, which is alternating, is just a map from the exterior square of the sheaf of differentials to the structure sheaf. Now, okay, we also have the Jacobi identity. And we have the following observation. So given that our bracket is an alternating by derivation, the left-hand side of the Jacobi identity is an alternating triderivation. So there's some, intrinsically differential way of taking this map from the exterior square of the sheaf differentials, some linear functional on the exterior square of the sheaf differentials, and producing a linear functional on the exterior cube of the sheaf differentials. And this, of course, is supposed to vanish. Okay, so this is, you'll notice this is not a workable definition for most purposes, because I haven't told you how to actually produce this triderivation from the biderivation, and it's definitely not a very straightforward thing. And I'm not actually sure of any way of doing it other than going back to the idea of, yeah, we just look at these affine opens and check the Jacobi identity on every affine open. There are some nice consequences that do follow from this description. For instance, that whether you satisfying the Jacobi identity is a, you satisfy the Jacobi identity on a closed subscheme. And so particularly this means that you can be a little lazy when checking it, because once you've checked it on some big set, it's satisfied on the closure. Okay, so let's think about what a special case. And, the special case we're looking at is surfaces. So for surfaces, let's say smooth projective surfaces. Okay, well, for a smooth projective surface, the sheaf of differentials has rank 2, and therefore the exterior cube is 0, and therefore the Jacobi identity is automatic. So luckily, in the case we most care about, we don't need to know how to compute this triderivation, because it doesn't matter how we do it, we're going to get 0. And so therefore, a Poisson structure on X is just a morphism. Well, okay, the exterior square of the sheaf of differentials on a projective surface is the canonical bundle. And so we get a map from the canonical bundle to the structure sheaf. And such a thing vanishes on an anticanonical curve. I'm assuming that our Poisson structure is not identically 0, because that's not a very interesting case. Okay, so anytime we have something non-commutative generating something, if we have, so whatever our non-commutative surfaces are, when we relax them to something commutative, we have this Poisson structure surviving, which is basically given by this, which is essentially given by this anticanonical curve. Bigger, if I tell you the anticanonical curve, you get a map from the structure sheaf to the structure sheaf of the anticanonical curve, and the kernel of that is isomorphic to omega x. And so up to an overall scalar, that determines a Poisson structure. Let me give this a name, alpha. So in the anticanonical curve of Q, name Q, and so figure Q determines alpha up to a scalar. So modulo that small scalar freedom, having a Poisson structure is the same as having an anticanonical curve. So we see that in all of our cases, we get this anticanonical curve sort of naturally in the picture. And which tells us basically that we also get this Poisson structure naturally in the picture coming from this curve that tells us about our singularities. Okay, so as I said, this other thing this tells us that there's things we're missing, because on F2, which is the ruled surface corresponding to this, well, this canonical ruled surface we were talking about. The anticanonical bundle, or the anticanonical linear system, is H-dimensional. So what do they look like? Well, remember we have this weighted projective space. And, well, okay, there should be a constant here in principle. So the anticanonical linear system, I mean, an anticanonical curve, we can just write down the sections of that line bundle on F2, and we see that the sections, it's basically just a general equation of degree 4 in this weighted projective space. Okay, now there's one slight technical issue we should think about, which is we have a little bit more structure in the picture that we didn't actually talk about, but in each case, we have this dictionary going from equations or relaxations of equations to sheaves. But there's a special equation, namely the trivial equation. So for a differential equation, we take v prime equals 0. For a difference equation, we can take v of z plus 1 equals v of z. So there's always a trivial equation in the picture. And the trivial equation turns into a sheaf. And so in particular, the trivial equation corresponds to the singular point of this weighted projective space, which when we blow it up becomes a curve. Okay. But the trivial equation had better be non-singular, because we can write down, we understand its solutions. We know they're all homomorphic and invertible. It's not singular. So since this is not singular, again, we have this curve Q. Q can't meet it. I should say, when I say it corresponds to this curve, what I mean is, of course, it's a line bundle on that curve, but it's supported on that curve. Okay, but that sheaf has to be disjoint from Q, because that sheaf has no singularity. The equation has no singularities. And so therefore, A naught has to be a unit. And so without loss of generality, A naught equals 1. Okay. Now, I hate myself for doing this, but ignoring characteristic 2, we can complete the square. So now we're just taking y squared equals a quartic. And we get different cases from the factorizations of B4. So in particular, B4 equals 0 is our differential case. B4 is, let's say, x to the 4, or more generally, if it has some root with multiplicity 4. This is the additive case that we talked about earlier. And a B4 has two double roots. That's the multiplicative case. And you just check in each case, y squared equals x to the fourth has two factors, y squared equals x, y equals x squared, y equals minus x squared. And those two components are tangent. So it gives us that picture I talked about earlier. Okay. But there's three more cases. We can have a simple root and a triple root. Or we can just have one double root. Or we could just have four distinct roots. Okay, now we can draw a picture of what the curve looks like in each of these cases. So here, the curve has a cusp. Here, the curve has a node. And here, the curve is essentially an elliptic curve. Okay, so this tells us that we need to have an interpretation, or we want to have an interpretation of these cases in terms of equations. Now, here, the easiest way to do this is to cheat and say, okay, well, I already know that there's an interesting family of equations because I've worked out a very special solution of elliptic pendulum A and figured out what that lattice pair has to look like, and that gives me an elliptic difference equation with a little bit of extra structure. But the other way of looking at this is, so we have this curve, or curve Q, and Q, of course, has a normalization. We can just, if it's singular, we blow up the singularity. We get Q tilde. And the idea is we base change from P1 to Q tilde, or in other words, we replace our surface X by the double cover induced by Q tilde goes to P1. And this, of course, is a ruled surface over Q tilde. And what does the surface look like? What does the new anticanonical curve look like on this base change? I mean, basically, the preimage of Q is just going to be the new anticanonical curve. And so what it looks like is, well, two tangent components, two components meeting in two distinct points. And then, well, okay, in this elliptic case, Q tilde is elliptic. And so we get this new ruled surface is basically E cross P1 now. And so we get two copies of this elliptic curve. Or in other words, when we do this base change, we get a difference equation. I mean, we get a sheaf that we can then turn the crank to turn it into an equation. Okay. Now, of course, there needs to be some extra structure there. But this comes from the fact that we did this double cover. And so, there's an evolution acting on this picture. There's an evolution acting on Q tilde over P1. And that evolution, well, it doesn't change this pulled back sheaf. I mean, it actually gives you, there's actually an equivariant structure on the pulled back sheaf. So it comes with a natural map from the pullback through the involution of M to M. Okay, and that means that when we turn the crank, we get a relation between A and the doohickey an analog of A corresponding to the pullback of M through the involution. And so what we see is that the involution this is in some ways easiest to see. Oh wait, no. Sorry, yeah. So the involution takes Z to minus Z, or 1 over Z in the multiplicative case. And so what we find is that we get an equation. So let me talk about just the ordinary additive case first. But there's extra structure. So that A of I think it's -1 minus Z is up to a change of basis, the same as A of Z inverse. Now, this is a little annoying to have this matrix C in there, but we can rephrase this a little bit. By basically saying, okay, well, let's sort of try to undo this relation and see what it actually corresponds to. What we see, what it corresponds to is basically imposing a symmetry, a twisted by C symmetry on our solutions. And then we have the following theorem, which is one of many theorems called Hilbert's theorem 90. But it's a relatively straightforward case of Hilbert's theorem 90, which tells us that C can be factored so yeah, this may be a different C, but the point is there's a consistency condition that has to happen. So C of minus Z ends up having to be equal to C of Z for this to make sense, for the second equation to make sense. Sorry, inverse. So, and the Hilbert's theorem 90 tells you if you have a matrix which is taken to its inverse by some involution, then it actually factors in a way that explains that property. So if you take anything that factors like this and negates Z, you get the inverse. And so the Hilbert's theorem 90 tells us that that's the only way that happens. This of course looks very little like many of the more familiar versions of Hilbert's theorem 90, but in the end, it's just basically it's a relatively basic statement about Galois cohomology, in this case with coefficients in GLN. Okay, and so we can change it. So in particular, using Hilbert's theorem 90, we can eliminate C. And so we get what I call a symmetric ordinary difference equation. Which is really the pair of equations with the consistency condition that A is taken to its inverse by basically the involution, or this slightly twisted involution. Okay, now the reason I'm writing it as this system of equations is that what it means to be singular for a symmetric equation is a little more subtle than what it means for it to be singular if you just forgot the symmetry. And of course, we could always just forget the second relation and get an ordinary non-symmetric difference equation, and that's where that's singular. But this turns out to be the wrong thing because, as an example, the equation V of Z plus 1 equals minus V of Z is non-singular if we forget the symmetry, but this has no, it's a first order equation. If it's going to be non-singular, it has to have a non-zero holomorphic solution. But it has no non-zero holomorphic solution near z equals minus a half. Because if you put these things together, sorry, let's say z equals a half. I guess it doesn't actually matter in this case. But if you combine those two equations, you get v of 1 minus z equals minus v of z. So a holomorphic solution, a solution which is holomorphic near a half, has to vanish at a half. And so we don't get any non-zero holomorphic solutions, and therefore this is singular. So this is a more subtle thing, and this means that we really do get something new, from this symmetry. I mean, the first thing, of course, is that if you treat it as a non-symmetric equation, you're typically going to have like twice as many singularities as you thought you have, because it's easy to see from this that the zeros of A and the poles of A are related by this symmetry. And so if you want to have if you want to have 8 singularities, you'd rather better have 8 zeros and 8 poles, or else it'll be a lot less singular than you thought it was. Okay, and so we get 2 more cases. Symmetric Q difference is the same, except we work in the multiplicative group, and symmetric elliptic are both analogous. Okay, and so the upshot so far, every Poisson structure, or every, I'm putting in quotes because we have to have this, we want to have this nice section that's disjoint from where the Poisson structure is non-zero. On this particular ruled surface, is an interpretation of sheaves as equations, or as relaxed equations. Sorry, we need to say how we do this in the symmetric case. So in the symmetric case, well, we have this symmetry, and let's do our usual thing of taking our translation to be trivial. So the Higgs version of this is just a matrix such that A of minus the inverse is equal to A of Z in the ordinary elliptic case, analogous in the multiplicative case. And so therefore, this factors, again by Hilbert's theorem 90, in this particular form for some B. And again, there's a minimal factorization. So now B well, it's no longer just something living on the base curve. It really is living on Q. So let me give a name for our map from Q to P1. Call it pi. And what B is, most naturally, is a map from the pullback of E to the pullback of W. Okay. And then once we've done that, we can do the adjunction, say that, hey, yeah, that tensors W by O0 plus O minus 2, and turn the crank and get something on our ruled surface. The other thing we can do is say, well, B lives on Q. So it has coefficients, because, well, V and W are just vector bundles on P1. Those are very simple sorts of objects. So we can actually turn this into an honest matrix. We just need to be careful about what degrees we take. And the coefficients live in a quotient of this graded algebra corresponding to our weighted projective space. Okay. And the observation is that we can write any such element canonically can be written as y times b1 plus b0. Because anytime we see a y squared, we can mod operate the equation to get rid of it. Okay, but this is exactly what the coefficients, so we just take that matrix on the weighted projective space, and the co-kernel of the matrix is our sheaf. And this automatically has the property that when we restrict to Q, it recovers B, and we're singular where the determinant of B vanishes. And therefore we're singular where the sheaf meets this appropriate anticanonical curve Q. And it's not too hard to see that you can actually give a similar description for the other cases as well. I mean, you can, because we're always just modding out by this y squared equals something. And so you can always get a similar description. Okay, so as I said, the upshot is that we get every one of these ruled surfaces and every Poisson structure on that ruled surface with this mild technical condition gives rise to a dictionary between sheaves and Higgs bundle type objects corresponding to some type of equation. Okay, now there's a couple of loose ends. Where is this? Why do we get this minimality? Well, so there's a nice observation. Namely, if our factorization were not minimal, we'd still get a sheaf. Because the sheaf just cares about we have these two matrices. It doesn't care at all about whether this factorization is minimal. And non-minimal basically implies that the sheaf, or is equivalent to, in fact, the sheaf has a vertical component. So in other words, if we think of our, we have this ruled surface, and we have this sheaf on the ruled surface, which is supported on some curve. Our factorization is minimal if and only if the support of the sheaf does not contain any fiber of the ruling. And then it's not too hard to see that if it does contain a fiber of the, if it does contain a fiber of the ruling, you just throw away that part of the sheaf and turn the crank back, and you'll see that you actually get the same equation. And so although the formal process involves choosing a minimal factorization, you don't have to. You can, if you just want to know what sheaf do I get, and we'll see later why you might want to know what sheaf you get from a particular equation. All you need to do is take any legal factorization, turn it into a sheaf using this procedure, and then check for vertical components that you then throw away. And you don't even need to be too careful about how you throw away the vertical components, because it turns out if you throw them away the wrong way, you'll get something which is isomonotony equivalent to the original equation, which will normally be good enough anyway. So this is the general sort of procedure. Okay. And in particular, this is one way you can prove that there really is a minimal factorization, because it's clear that there is a canonical way of throwing away vertical fibers. Okay, now, right. So this is our general framework, but there's a bit more one should think about. So the first thing is, there are other ruled surfaces. And some of them still have Poisson structures, so we ought to have some idea of saying what's going on with them. Now, what we can always do is we can always choose a section S naught. Now, right, so we're going to choose a section X naught. And then what we're going to do is we're going to say, well, S naught, okay, we can't really say that it corresponds to an equation because we're on this weird ruled surface that's not one of this very special kind. But, we should still assume we have a Poisson structure. And so S naught, there's this curve Q, and S naught meets Q. And we can choose S naught to not be a component of Q. This is a very weak condition, of course. And what we're going to do is we're going to blow up a point where S naught meets Q, and then blow down the corresponding fiber. Okay, so when you do this procedure, the blowing up turns one of your fibers into a pair of curves, and you can check that they're both -1 curves. And so the one you got by blowing up, you can blow down the other one, and that'll of course collapse you back to being just a fiber. So this gives you a new rule surface. And one can check that this new ruled surface is still Poisson. So basically, the general rule for Poisson surfaces and blowups is if you can always blow up a point of the corresponding anticanonical curve, and you can always blow down a -1 curve. And so in both of those cases, there's an induced Poisson structure. And it's basically, in some sense, it's clear that there's at most one induced Poisson structure, because we can always just say, well, there's a Poisson structure on the function field, and we're not changing the function field. The only thing that could happen is it might fail to be holomorphic. And then you just check that blowing up a point of the anticanonical curve does not introduce a pole to the Poisson structure. Okay, so this is still Poisson. And so we keep going. And what we see is that eventually, S naught is going to be disjoint from the resulting anticanonical curve. Every time we do this, when we blow up the point, we reduce the intersection by 1. And then blowing down the fiber doesn't increase it. And so the number of steps we have to do is just the intersection number of S naught and Q. Okay. And then we just check modulo an annoying case that only happens in characteristic 2. So we can feel free to ignore for the most part. This forces X prime to be our favorite ruled surface. So given any sheaf on, so the other thing we need to say is that we can carry through, we can carry along our sheaf. Now, since we're in commutative land, we can cheat a fair bit. Our sheaf is supported on a curve. And so typically what we can do is we can just move the curve, because we get this rational map of the curve. So we just move the curve around and then take the same sheaf on the new curve. This occasionally breaks, but there are ways of fixing this. And moreover, there are ways of fixing it that don't need to talk about the support of a sheaf, which it turns out breaks horribly in the non-commutative case. You ideally don't want to do that. So what we get is we get a new sheaf M prime on X prime, and thus we get an equation, or a equation modulo the relaxation bit. So we see that for any ruled surface and any section which is not contained in the anticanonical curve, we get a dictionary from sheaves on that ruled surface to Higgs type bundles. Okay, now what happens if we change the choice of section? Well, in that case, what we see, and we will see this in more detail later, but this turns out to basically gauge the equation. So it's slightly different because we're not actually about equations. But basically what we're doing is we're essentially multiplying v of z by a scalar valued function that satisfies a first order equation. Because S naught prime, well, if you take the structure sheaf in S naught prime, that by this procedure together with S naught determines an equation. And what we're doing basically is tensoring that first order equation by the equation corresponding to M prime, and that's all it does to the equation. So we basically get V prime of Z equals, in the differential case, basically A of Z plus U prime over U V of Z. So U satisfies this nice first order equation. So we're just doing a very mild transformation. So in general, sheaves on ruled surfaces, Poisson ruled surfaces, correspond to equations up to scalar gauge. Or if you like, it corresponds to projective equations. So for instance, the other way you could, there's a fairly natural way you can kill off this freedom, namely you say, okay, well, A lives in the Lie algebra GLN, and so we just take the map from that to the Lie algebra PGLN, and hey, that kills off this annoying scalar we added. Okay, and we can't really avoid this scalar gauge freedom because if we had a translation that would work in general, there would be a trivial equation which would give us a section disjoint from the anticanonical curve. And on a general Poisson ruled surface, there just aren't sections disjoint from the anticanonical curve. So this never really works in general. Okay, now I want to mention one theorem. If X is a Poisson surface, then either X is symplectic, i.e., the Poisson structure viewed as a section in the canonical bundle is actually an isomorphism, so it trivializes the canonical bundle. So a symplectic surface just means trivial canonical bundle. It's more complicated if it's not a surface, but okay. Or B, there is a birational map from X to Y such that Y is our favorite type of ruled surface. In particular, this includes having a section disjoint from the anticanonical curve. And the Poisson structures agree generically. This theorem uses the classification of surfaces, so it would go a bit beyond really the subject of these lectures. But basically, you can show that having an effective anticanonical bundle rules out almost all of the surfaces that birational equivalence classes of surfaces you might have. And then you basically say, okay, if it's either symplectic, in which case there's nothing to do, or it's Poisson, in which case you choose a section, do this game of making the section disjoint from the anticanonical curve, and then check that actually forces it to have this structure. And when I say that, well, again, I mentioned this annoying characteristic 2 case. This is not quite true in characteristic 2. There's like one extra case you can get where C is elliptic and the vector bundle that you're taking is the self-extension of the trivial bundle. And then there's this twice-isogenousous curve in the picture, but it's a little weird. And as I said, only characteristic 2, so we can pretty much ignore it. Okay, so the upshot is that basically, except for symplectic surfaces, which are don't seem to work nicely for this theory, every Poisson surface, there's a way of interpreting it sheaves on that surface as equations. Now, the tricky thing is that that way of interpreting it is not unique. So we have the very important example of P1 cross P1. And the reason why this is important, so, and this is really encapsulates sort of all of the things that are both hard to deal with and very nice about the rational case. And the point is, P1 cross P1 is a real surface in 2 different ways, because it has 2 maps to P1. And so if we choose a section of one ruling, we get an interpretation of sheaves as equations. If we take a section of the other ruling, we get an interpretation of sheaves as equations. So in other words, up to scalar gauge, we get 2 interpretations of sheaves as equations. Assuming we've chosen a Poisson structure. Okay, and these interpretations can be very different. So there's a few things we can say fairly directly from this theory. So the first thing is, well, so the support of M, which in the differential case is called the spectral curve, so we might as well still call it the spectral curve. I should say a lot of this theory is at least implicit in the differential case, although often they'll just directly work with the spectral curve and not necessarily talk so much about the actual surface that it naturally lives in. But there's a couple of observations. So firstly, the order of the equation i.e. the rank of the vector bundle is the degree of the support of M over the base curve. And you just basically look at the theory here and you say, okay, well, yes, I'm constructing this matrix B, which is, linear in, let's just think about the P1 case, linear in Y, and it's an n by n matrix up to with appropriate degrees in X and W. So when we take this determinant, we get something which is degree n if it's a rank n vector bundle in Y. And so indeed, for any choice of X and W, up to any homogeneous coordinate XW, we get n different choices of preimage in this determinant. Okay, and so we can recover the order of the equation just from very simple geometric information. But that's the order relative to this ruling. And so for P1 cos P1, of course, we have a different ruling. And so, for instance, if M looks like this parabola in P1 cross P1, it's degree 1 with respect to one of the rulings, and degree 2 with respect to the other. So this transformation can change the order of the equation that we get. I mean, the swap the two rulings and then reinterpret it changes the order of the equation in general. But there's more. We have this anticanonical curve in the picture. So let's consider this particular case of, sorry, this is not the example I wanted. Consider this particular choice of anticanonical curve. I should say on P1 cross P1, anticanonical just means biquadratic, which of course, those of you who are familiar with integral systems will be saying, hey, biquadratics, I've seen those before. Well, yeah, there's a reason why, these things show up a lot. Okay, so you get this biquadratic equation. And this has, we see things in two different directions. So with respect to the one ruling, with respect to the vertical ruling, it meets every point, it meets the curve twice on generic fibers. And so what's going to happen when we take a, therefore, horizontal section and blow up the points of blow down fibers is this vertical fiber is going to get blown down. Because our whatever red section we pick is going to have to meet that vertical fiber. So it's going to get blown down. And so this is going to turn into that nodal curve we had before. And so relative to the vertical ruling, we get a symmetric Q difference equation. However, there's the other rulings. Let me rotate the picture. So let's consider what was the horizontal ruling. Okay, well now, when we choose our section, we're just blowing up smooth points and blowing down fibers. Nothing's going to happen. When we blow up this point here, now we have these 2 - 1 curves, but they meet different components of our anticanonical curve. And so when we blow down either one of the -1 curves, we're not going to be making our components meet. And so this turns into a non-symmetric Q difference equation. Okay, so we actually get qualitative changes. For instance, there's another one which is very familiar in effect, is this anticanonical curve. So we have a double component vertical and then two horizontal components. So this, on the one hand, vertically, this is additive, or a non-symmetric additive equation. But in the other direction, it's differential. So I should say, the rule in these cases for figuring out what qualitative type of equation you get is you look at how a generic fiber of your ruling meets the anticanonical curve. If it meets it in a double point, well, that means you have a non-reduced component and it's differential. If it meets it in 2 points, then the question is, are they on the same component or are they different components of the anticanonical curve? If they're on different components, you get a non-symmetric equation. And the type of the equation depends on whether the two components are tangent or meet in 2 distinct points. And if you only have one component, or if you only have one non-vertical component, then you get a symmetric equation, which is additive, multiplicative, or elliptic, depending on whether your curve is cuspidal, nodal, or smooth. So there's a very simple thing. But you could always, if you forget this, you could always just do this procedure of pick a generic section of the ruling and see what happens when you blow up those points of intersection and blow down the fibers. Okay, so this turns a non-symmetric additive equation into a differential equation. And this is, well, it has several different names. One of them is the Mellin transform. The other is the power series method. By which I mean, if somebody hands you an ODE, a linear ODE with rational coefficients, and asks you to solve it, one of the ways of solving it is the power series method, where you basically just say, okay, well, let me try to just write down what the power, a power series solution. And what you find when you do this procedure is that the coefficients of the power series satisfy recurrence. The value at your point, the value of the derivative of the point, value of the second derivative, so on, satisfies a recurrence. And that recurrence, modulo getting the scales right, you probably have to like double the second derivative and multiply the third derivative by 6, etc. But anyway, modulo getting the scaling all correct, you get a recurrence. And that recurrence, a recurrence is just a fancy way of saying an ordinary difference equation, or possibly the other way around. And so if you just ask for what are these coefficients of the power series, or what is the recurrence satisfied by the coefficients of the power series of a general solution, that's exactly this transformation. So, this is a very familiar sort of transformation, and we see that's a purely algebraic procedure. And that's actually the case in all of these things we can do. I mean, of course, in the commutative relaxation, it's always an algebraic procedure because we're just taking sheaves and changing the surface and turning it back into a Higgs type bundle. And there's some technical issues having to do with the fact that, well, a sheaf might be minimal with respect to one ruling, but not minimal with respect to another ruling. So things can get a little, there are some edge cases where things don't behave quite as well as you expect. But the commonality, we basically have, each case is at least formally an integral operator. And in particular, I often call this the Fourier transform. And of course, a big part of why I call it the Fourier transform is because the case where the most degenerate case, where you have a double vertical component and a double horizontal component, when you turn the crank, it's turning differential equations into differential equations. And it really is basically turning multiplication into differentiation and vice versa once you sort of undo the relaxation. So we get these various different Fourier transforms. And I will stop here because I'm at about a little bit past the 90-minute mark, and ask for questions.
This is a very, very powerful way of seeing Black's pairs. I was wondering whether you might comment on some cases that have been talked about in the literature where people write down Black's pairs that turn out to be, what do they call it, fake. Sometimes when people write down, I guess this is more in the PDE setting rather than the ODE setting.
Oh yeah, I know nothing about PDEs. But,
no, but sometimes people write down Black's pairs. They propose a lax pair, and it turns out that there's a gauge transformation which will take away the spectral dependence, and so you really don't get mapping to either spectral or monodromy space. Do you have any maybe degenerate cases where that could be the situation?
Well, this sounds like it might be related to apparent singularities again.
Yeah.
But I mean, certainly, I mean, that certainly could happen in a case with apparent singularities, where you start with something that has, 8 singular points, but if 2 of them happen to be able to cancel out, then that turns into an equation with a sort of with sometimes the way they cancel out is sort of only up to scalar gauge, and you would need to scalar gauge that away to get the full benefit of killing the apparent singularity. So that could be something along those lines. But nothing directly like what you're talking about really springs to mind. I mean, if you show me a specific example, I might be able to, turn the crank and see what's going on algebraically. But
sure, thanks.
Yeah, sure. Or even better, I can tell you how to turn the crank.
I have a question.
Sure.
So when you say an interpretation of shapes on rational surface as equations, what does it mean? So it's not an equivalence, right?
Well, right. So basically, so firstly, they have to be one-dimensional sheaves to correspond to equations. The other thing is they shouldn't have the other thing is you need, as we started to see here, you need to choose a ruling on your rational surface.
Yes.
Okay, and then your sheaf shouldn't have any vertical components. Okay, but given that, and up to this overall scalar gauge freedom, you can turn the crank and get a Higgs bundle type object. In fact, actually, if you're willing to talk about twisted things, you don't even have to do the scalar gauge freedom. There's a way of talking about a twisted Higgs bundle that you actually, and that really does give you a twisted Higgs bundle.
But is the interpretation injective?
So from equations to sheaves is injective.
Okay.
From sheaves to equations is bijective if you forbid them from having vertical components.
Oh, I see.
Actually, that's not. No, and there are modulo. There might be some issues with points.
But basically injective, you mean?
But yeah.
Oh, I see. Thank you. And I also have another question. So on this last slide, when you say it is Mellin transform or power series method, what does it mean since you are working with Higgs bundles, right?
Well, right. So what I mean when I say that is, you take the Mellin transform or the Fourier transform, write it down in an algebraic way. So it's basically it's turning certain multiplication operators into certain differential or difference operators, and certain difference operators or differential operators into multiplication operators. So you take that and then do a commutative relaxation.
Oh, I see.
And then you look at the geometry of that picture and it turns out to be this. Or the other way, I mean, the fancier way of seeing it is in the non-commutative picture, it really is doing this operation on operators. And the anti-canonical curve really does have this structure with respect to the two rulings of your non-commutative P1 cos P1.
Oh, I see. So you will talk about that non-commutative picture
At some point.
Oh, okay.
Probably.
Yes.
Once I've scared away all the people who, once I've scared away all the people who are shaky on outrage geometry or who don't want to deal with derived categories and all that nonsense so much. But yeah. So, possibly day 10.
Okay.
I don't know, but I don't know. I'm not sure how much I'll get through because already the commutative picture is something like 100 plus pages, and then there's 100 pages of non-commutative picture. So there will have to be some tasting menu part of this, as opposed to I won't be able to cover everything.
Also, in this setup, do you have some Kobayashi Hitchin type interpretation? So you mean if you have a Higgs bundle, you can somehow interpret it as connection?
Yeah, no, so that's a weird differential geometry thing. I mean, because my understanding is that only works C infinity land. It does not work analytically. I could be wrong because this is definitely not my forte. I mean, I try not to think that much about the differential case because you have to talk about these non-reduced schemes. But that's my understanding, is that there's it's not an analytic relation between the moduli space of Higgs bundles and the moduli space of connections. It's a slightly less. I mean, it's only smooth. It's not analytic. But that's I could be wrong. But it's definitely not algebraic.
Yeah, not algebraic. Yes.
Yeah, and I don't know anything like that for the discrete cases.
I see.
I mean, it's well. The tricky thing is, if you're dealing with non-compact things, it's very hard to show that they're not biholomorphic. And it's especially hard, I mean, it's pretty much impossible to show they're not C infinity equivalent. So
sorry, why are you speaking about non-compact case? Since you are allowing.
Well, because that's where when you talk about the moduli space of Higgs bundles, there's a transverse. Oh, sorry, I should say there's one more condition on the sheaf. It has to be transverse to the anticanonical curve.
Oh, I see.
Because otherwise, basically, what you're going to happen is that B naught is not one of your factors is not going to, your matrix B is not going to have full rank. And so when you try to do the inverse, when you try to invert B infinity or what have you, it's going to cause problems. I mean, you can't even say what it is generically in those cases. So there's that extra condition that it has to be transverse. And that means you're really looking at a non-compact moduli space because of that. And there's weird biholomorphic maps between non-compact moduli spaces out there. Yeah, even for surfaces. It's like, in fact, one of them shows up in Pan-Lavey. The space of initial conditions for Pan-Lavey is algebraically not constant, but holomorphically is, as you change lambda, something like that.
Yeah, I have another degenerate question.
Okay.
Which is, what happens if you were looking at QRT, for example?
Aha. So this is sort of this is spoilery, if you will, but the goal is to understand Pan-Lavey. But of course, we've given up on understanding Pan-Lavey because we did this commutative relaxation. But there's still an integrable system in the picture. And that integrable system is now basically isospectral instead of isomonodermy, and it's autonomous. And if in the Pan-Lavey case, it's QRT. Although QRT done in a weird looking way. This has to do with the fact that I'll be mentioning later that there's like infinitely many different lax pairs for Pan-Lavey, most of which have not been written down.
Yes.
Obviously, but I mean, when I say most of them have not been written down, I mean, as far as I know, only one of them has been written down. for any of the Painlevé equations. You know,
No.
or basically only the rank 2 ones have been written down.
The right 2 ones. Okay.
Yeah.
Good.
Basically for any, well, I'll say more later, but for any rational number, there's a lax pair for Painlevé, which is basically rank 2R degree D vector bundle. And then and then there's sort of a one case off at infinity, which is Sakai's interpretation.
Yeah.
So and then similarly, something like that also happens with QRT. So the actual QRT is sort of the thing corresponding to infinity, but then you have a different a lax parish interpretation for every rational number.
So you were saying if you did the commutative relaxation, then you would find QRT.
Yeah, in the case where you're second order transformation.